Welcome back to the deep dive. Today we're looking at a shift in artificial intelligence that, well, it makes everything we've seen so far look a little bit static.
Oh, absolutely. It's a massive leap.
Yeah, because we've spent the last few years being incredibly impressed by AIs that can talk to us. You ask it to write a poem or uh, summarize a long email, and it does it. But we are rapidly moving into the era of the autonomous agent, AIs that don't just chat but actually do things.
Right. It's the difference between asking a colleague for, say, a bit of advice on a project and asking them to just go and handle the entire project for you.
Exactly.
We're talking about agents that can navigate a website, buy a specific shirt for you, solve complex visual logic puzzles, or even engage in social negotiations. And they do this without you having to press a button for every single step of the way.
But that transition moving from a passive chatbot to an active agent, it isn't just a matter of, making the underlying model bigger. It turns out that training an AI to act autonomously introduces this really massive engineering hurdle.
It really does.
And the research we're digging into today for you circles around one central villain in all this, which is known as the credit assignment problem.
Yes, the credit assignment problem. This is basically the classic headache in what we call agentic reinforcement learning.
I mean, how would you break that down for someone?
Well, to understand it, imagine you're playing a really long, complicated game of chess. You make 50 different moves, and at the end, you win. Great.
Right.
You get the victory.
But the AI has to figure out which specific move actually caused the win.
Was it the pawn you moved in the very beginning? Or that risky knight sacrifice in the middle? Or did you just win because your opponent blundered on the last turn?
Exactly. In traditional AI training, the agent only gets a signal at the very end of the game. It gets a 1 for a win or a 0 for a loss. We call this a sparse reward.
Sparse because it's so rare.
Right. The agent spends the entire game just stumbling around in the dark. And only at the absolute finish line does someone yell, good job, or fail.
It makes learning incredibly slow, I'd imagine. It does. Because the AI has literally no idea which of its 50 steps were the brilliant ones and which ones were just terrible mistakes that it somehow happened to survive.
It's like trying to learn how to cook a delicate souffle, but the only feedback you get is...
Just tasting the final dish.
Yeah. You don't know if you whisk the eggs wrong or if you set the oven temperature too high. You just pull it out of the oven and know that it collapsed.
That is a perfect analogy. You just see the collapse. In today's paper, which is titled Agentic Reinforcement Learning with Implicit Step Rewards.
Or iStar for short, which rolls off the tongue a bit better.
Much better. So iStar proposes a solution to this souffle problem that is, frankly, just elegant. They've figured out a way for the AI to effectively grade its own homework step by step without needing a human looking over its shoulder the whole time.
And the results they're claiming are state-of-the-art, not just in simple little toy games, but in complex reasoning tasks and even weirdly open-ended social situations.
Which is the hardest thing to train for.
Right. So let's unpack why the old way was failing so hard. We know these new agents are being built for what the industry calls long-horizon tasks.
Yes, think about a software engineering agent. It has to write a chunk of code, execute it, see an error message, debug the code, rewrite it, and then run it again.
That is a lot of steps.
That's a trajectory, a very long chain of reasoning and actions. If we rely on that final outcome-only reward we talked about, we get what's called high variance.
High variance meaning the AI is basically just wildly guessing.
It's throwing darts in the dark. It might get lucky and win one time, but since it doesn't know why it won, it completely struggles to replicate that success.
So how is the industry trying to patch this before iStar came along?
Well, the main patch was something called process supervision. The logic makes sense on paper. Instead of waiting for the end of the game, let's just give the AI a little treat for every single correct step it takes along the way.
Like leaving a trail of breadcrumbs for it to follow.
Exactly.
But I have to assume the catch is, who is out there baking all these breadcrumbs?
That is the million-dollar question. To give step-by-step feedback, you traditionally need human beings to sit there and label everything. Someone has to say, this step was good, that step was bad.
Which is prohibitively expensive and slow.
Very slow. So, to speed it up, researchers tried using another AI to grade the steps, an LLM as a judge.
But then you just have one AI potentially hallucinating grades for another AI. That sounds messy.
It gets incredibly noisy. And worse, the agent actually learns to hack the reward. It starts doing things that look good to the AI judge, but don't actually solve the underlying problem.
So we were basically stuck between a rock and a hard place. We either had the blind guessing of sparse rewards or the extremely expensive micromanagement of process supervision.
Precisely. Which brings us to iStar, implicit step rewards for agentic reinforcement learning.
Let's focus on that word implicit. That seems to be doing a lot of the heavy lifting here.
It really is the core of it. iStar doesn't need a human to label the steps, and it doesn't need an external AI judge. It uses a self-reinforcing loop. The system is actually training two things simultaneously.
Okay, what are the two things?
First is the policy model. That's the actual agent out there doing the shopping or solving the puzzle. And second is an implicit process reward model, or PRM.
So it builds its own internal critic.
Exactly.
But wait, if the agent doesn't know what it's doing yet, how does the critic know what to grade?
This is the clever bit.
Yeah.
It relies entirely on hindsight. The system looks at complete trajectories. Let's say the agent tries to solve a spatial puzzle. It tries once and completely fails. That's recorded as a negative trajectory.
Okay.
Then it tries again, a totally different approach, and it succeeds. That's a positive trajectory.
So now it has a recording of a clear win and a recording of a clear loss.
Correct. And then iStar uses a method called trajectory-based DPO, which stands for Direct Preference Optimization.
Right, DPO.
It compares the winning tape side by side against the losing tape. The model effectively works backward from the win. It deduces, mathematically, hey, these specific actions in the winning run were the key deviations from the losing run.
Oh, that's fascinating. It's acting like a detective at a crime scene. It looks at the body, the final result, and reconstructs the exact steps that had to lead there.
That's a great way to visualize it. It assigns an implicit step reward to those specific actions. It infers the value of the step solely based on whether it appeared in the winning chain. It asks itself, what did I do differently this time? And then assigns value to that specific difference.
That seems so much more efficient than waiting for a human to review the server logs. But I noticed the paper made a really strong distinction here between step-level rewards and token-level rewards.
Yes, that is crucial.
They compared iStar to a baseline method called prime. Why does that distinction between step and token matter so much?
It's all about the zoom level. An LLM generates text token by token, which are basically just parts of words. Methods like prime try to assign a reward to every single token it spits out.
That feels too zoomed in. It's like grading a high school essay by looking at every individual letter the student wrote instead of reading the sentences.
Which creates massive statistical noise. iStar, on the other hand, focuses on the step level. In these agentic tasks, a step is usually a solid chunk of reasoning followed by an action.
Like saying, I need to find a blue shirt, and then hitting search.
Exactly. Search. Blue shirt is one single step. iStar grades that complete move, not the spelling of the word shirt. It's the sweet spot. It's granular enough to actually be helpful, but stable enough for the math to learn from.
Okay, so we have this implicit reward. The agent has figured out which steps likely led to the win. But the paper mentions the agent doesn't just blindly follow these new step rewards. There's something they call the advantage calculation.
Right, this is the safety valve of the whole system. If you just chase step rewards blindly, the AI might find a loop of actions that feels good to the math, but doesn't actually finish the job.
Oh, you see this in video game AI sometimes. They find a glitchy spot to stand where they just rack up points forever, but they never actually beat the level.
Reward hacking. Exactly. So how does iStar prevent that? It combines two different signals. First, it calculates the episode advantage.
Which means, did I actually win the game?
Yes. And then it adds the step advantage, which asks, was this specific action better than my average behavior?
So it basically gates the credit.
It absolutely gates it. You only get credit for a good step if that step was part of a run that actually resulted in a success. It filters out all that loop hacking noise.
Let me make sure I have the training loop straight for you listening. The agent tries a bunch of stuff. A verifier checks if it ultimately won or lost. The PRM looks at the wins and losses to figure out why they won, generating these step grades. And then the agent updates its own brain to do more of those high-grade steps.
You've got it. And because it's a closed loop, it spirals upward. As the agent gets better at the game, the data it generates gets better.
Yeah.
And as the data gets better, the PRM gets better at grading. They literally pull each other up.
That is wild, but let's talk performance, because all this math is just theoretical until you put it out in the wild. They tested this on 3 main platforms: WebShop, Visual Sokoban, and something called Sotopia.
Which is a remarkably diverse set of playgrounds.
Hmm.
WebShop is a text-based Amazon simulation. Visual Sokoban is a spatial grid puzzle. And Zootopia is open-ended social interaction.
Let's start with web shop. This seems like the bread and butter for what people want autonomous agents to do right now, going out on the internet and buying things.
iStar absolutely crushed it here. It achieves a 94.7% score.
Wow.
For context, the baseline method, which was RLO, peaked at around 90%. But the real story isn't just the high score, it's the efficiency.
How fast did it learn?
It reached that peak performance in about 105 steps. That's almost twice as fast as the previous methods.
Which means it costs half as much compute to train it to that level. That is a huge deal when we're talking about the sheer energy and money required to build these things today.
Exactly. It's a massive cost saving. Then you have Visual Sokoban. Now this one is trickier because it requires spatial planning. You are an agent pushing boxes onto targets in a grid.
Oh, I know this game. If you push a box into a corner, you lose.
Okay, yeah.
Right? Because you can't pull it back out.
Exactly. High stakes, zero margin for error. You can't undo a bad move.
So how did iStar do there?
It hit a 91.7% success rate. The best baseline they tested was only around 86%.
That's a solid jump.
It is, and that gap represents the agent actually understanding the process. It didn't just get lucky by flailing around. It understood the sequence required to keep its options open and not trap the boxes.
But the result that really jumped out at me, and I think this is where the conversation gets a little sci-fi, was Zootopia.
Oh, the social test.
Yeah, negotiation, persuasion. There is no clear scoreboard in a conversation. How do you even measure a win in a social setting?
That's the entire challenge of Zootopia. Rewards in social settings are what researchers call unverifiable. There's no bell that rings when you've successfully been polite or persuasive.
Right. I started all that ambiguity.
When it was chatting against GPT-4o, the iStar agent improved its goal completion by 48% compared to the baseline.
48%. That is a massive jump in social
This
competence.
is huge.
And the notes mention it beat prompting frontier LLMs. Are we talking about small fine-tuned models here or the big base models?
The paper explicitly compares iStar's trained agent against prompting frontier models like GPT-5, Gemini 2.5 Pro, and DeepSeek R1.
And it won.
In these specific agentic benchmarks, yes, iStar outperformed them.
That is significant. It really implies that a specialized, somewhat smaller model trained with this implicit reward method can punch way above its weight class. It's beating massive generalist models that haven't been fine-tuned with this specific loop.
It completely validates the method. We're seeing that how you train the model is becoming just as important as the sheer scale of the model. You can have the smartest, largest model in the world, but if it doesn't know how to navigate the step-by-step logic of a task, a smaller, better trained agent is going to run circles around it.
I really want to dig into why this works under the hood. The ablation studies in the paper, where they essentially break the model to see what's happening underneath, showed something really interesting about the training dynamics.
They did. If you look at their graphs, the implicit step reward metric actually goes up before the episode reward goes up.
Meaning what exactly?
It tells us the agent learns the moves before it learns to win.
Interesting.
It picks up heuristics, good habits, shortcuts. Things like don't push the box in the corner or in web shop. Always check the price before clicking buy. It masters these little subroutines first, and then the overall wins naturally follow.
It's building a foundation of competence. It's like a kid learning to dribble a basketball before they even try to play a full game.
Exactly. And because of that solid foundation, the episode length actually drops over time.
So it solves the problem faster.
The agent gets smarter and lazier in a good way. It solves the task in fewer steps because it just stops flailing around. It knows exactly what to do.
There was one finding in the ablation study that seemed totally counterintuitive to me. They tried using the ground truth rewards directly from the game engine itself, like the actual real score. And it didn't work as well as iStar's imagined reward.
Yeah, that surprised a lot of people.
Why would a mathematical guess be better than the actual real score?
That is the most fascinating part of the paper. Real-world environments, or game engines, are incredibly rigid. They usually give harsh penalties for every extra step you take, or they are just very binary. iStar's learned rewards, on the other hand, were smoother. They actually adapted to the agent's current level of capability.
Oh, I see. So the PRM acts almost like a good human coach. It doesn't just scream at you for every single mistake. It gently guides you toward the behavior that will eventually lead to winning.
Exactly. It provides a much better gradient for learning. It translates the harsh binary reality of a win or a loss into a nuanced graded language that the agent can actually improve on step by step. It smooths out the entire learning curve.
It's so funny. We started this whole deep dive by talking about how hard it is to get good feedback without human labels, and we ended up finding out that the AI actually generates better feedback for itself than the actual raw environment does.
It really bridges that gap beautifully.
Mhm.
It solves the credit assignment problem by just letting the math deduce the value of the steps in hindsight.
So for you listening, the big takeaway here is that we are unlocking a completely new tier of training efficiency. This method removes the bottleneck of human data labeling. We just don't need armies of people grading AI homework anymore.
It's an accelerant for the whole industry. It means we can train agents for much more complex, longer tasks, things that take hundreds or thousands of steps, without the financial cost just completely exploding. We are officially moving from AI that passively answers your questions to AI that actively solves your problems.
Before we close out, I want to circle back to that Zootopia result, the social skills benchmark.
Oh yeah, this is the part that really lingers with me.
Because you have an agent that improved its believability and relationship scores by nearly 50%,
Mhm.
simply by analyzing the math of winning and losing trajectories.
Right. And we know the AI doesn't feel empathy, doesn't actually value a relationship with a GPT-4o judge. But iStar allowed it to deduce that acting empathetic or acting reasonable led to a mathematically better outcome in the negotiation.
It effectively derived a mathematical formula for social grace.
It did. And that raises a really provocative question for us to end on. If an AI is teaching itself social skills based purely on implicit mathematical rewards derived from winning, are we evolving agents that are genuinely socially intelligent, or have they just found a mathematical shortcut to hack our human social expectations?
Are they actually charming, or did they just solve the equation for charm?
Exactly. And perhaps more importantly, if the final result is that we interact with them and we feel heard and understood, does that distinction even matter?
Wow. That is definitely something for you to chew on the next time you find yourself surprisingly pleased with a customer service bot. You might just be a solved equation. That's it for this deep dive into iStar. Thanks for listening.